Hello everyone. In this final project for the course, our team will attempt to tackle the issues surrounding torque, power, work, and energy, and how they relate to cycling. Once again, I am Chad Cochran. My teammates are Katie Donnelly and Tori Anderson-Vale. Here's the cycling motion that we've been tasked to analyze. The values for a stationary cycle are much different than an outdoor road cycle would be, where elements such as wind resistance, weight of the rider, and terrain would all play a role in the forces a rider encounters. When focusing on how torque applies to the cycle motion, figure 1 with the cranks at the 3 o'clock position. Downward force on the front pedal has to be greater than downward force on the rear pedal in order for the bike to be propelled forward. With cranks at the 6 o'clock position in figure 2, pressing down on the top pedal won't theoretically cause the cranks to rotate, but in practice it does because this position is rather unstable. In picture 3, downward force on the top brake as well as an upward force on the rear brake will also cause the rotation that were desired. In picture 4, with the cranks between the 4 and 5 o'clock positions, similar to picture 3, a proportion of the downward force applied to each pedal will affect this rotation. Using less massive pedals and shoes will decrease the momentum of inertia, which will increase the angular velocity, especially in the backstroke phase. The main application of force to the pedals is in a downward thrust, which comes naturally. The technique of drawing force across the bottom of the revolution arc and upwards to the start of the downward thrust is popularly referred to as ankling. Common errors in performance can occur if the rider does not complete total downward and upward force. Improper bike adjustments, the correct body position on the bicycle, and a good pedaling technique are necessary to prevent cycling injuries and to optimize force distribution during the pedal stroke. The concept of ankling can be seen here. Work and power are two very important topics when discussing biomechanical advantage and predicting the success of any particular exercise. Cycling is no different. We can even break down each muscle to determine its role in the overall cycle motion, but utilizing the overall power and work outputs seem to demonstrate the concept much more clearly. Units are something that are necessary here, and you should be paying attention to. Work, for instance, is measured in joules, not Newton meters, although 1 joule is equal to 1 Newton meter. Power can also be confusing, measured in watts, after James Watt, which is equivalent to producing 1 joule of energy per second. If you've ever paid attention to the stationary cycle, the display can often tell you your speed, distance, power output in watts, and calories. How do these values get calculated though? The easiest way I thought to illustrate this point was through a good old-fashioned word problem. So let's use a 100 kilogram man that rides for 10 minutes with a resistance of 50 newtons and averages around 80 revolutions per minute. Also important to know is that 1 revolution equals 5 meters. Doing this calculation for a road cycle, weight of the rider, elevation, and gear of the bike would all need to be taken into account and would change the force and therefore everything else. Other variables such as crank length, tire circumference, and seat height can also play a role in these calculations, which would be most important to elite competitors. So let's get started. So your force here is 50 newtons. Your distance covered here is going to be around 4,000 meters or 4 kilometers. The work you put in, which is your force times your distance, is going to be roughly 200 kilojoules. And your power, which is going to be your work divided by the time, is about 333 watts. To put this into perspective, according to Voigt in 2007, average power outputs during a certain segment of the 2005 Tour de France range from 218 to 234 watts, depending on the train. So to figure out the energy usage for our individual, it's important to know that 1 calorie is roughly equivalent to 4.2 joules, meaning that 1 kilocalorie, or a food calorie that we actually think about, is roughly 4.2 kilojoules. So from our previous example, our rider performed roughly 200 kilojoules worth of work, which can be translated to 48 kilocalories in 10 minutes, right? Well, not so fast. According to David Wilson, a mechanical engineering professor at MIT, we are only capable of being roughly 20 to 25% efficient on the bike, losing the rest as heat. Correcting for this, our actual calories burned, depending on efficiency, would be somewhere from 190 to 240 calories in 10 minutes, or about 1100 to 1400 calories per hour. When pedaling a stationary bike, metabolic energy is converted into rotational kinetic energy. The amount of rotational kinetic energy the bike has depends on the moment of inertia and angular velocity of the wheels. When pedaling a non-stationary bike, metabolic energy is converted to both rotational and translational kinetic energy, which again depends on the moment of inertia, angular velocity, and now the mass and linear velocity as well. Increasing the mass, be it in the wheels, bike frame, or rider, would cause a decrease in rotational and linear velocity. It has been shown that age affects cycling efficiency as well. As athletes age, the ratio between work performed and energy expenditure decreases. This means that metabolic energy of older athletes is less efficient in converting them to mechanical energy. While a collision is highly unlikely during stationary cycling, it is all too common in the outside world. The outcome of a collision is usually dependent on the conversion of momentum. A car has much more mass and usually more velocity than a bike, giving it overall larger momentum. This means that after a collision occurs, the car and the bike will travel in the direction the car was going, which is bad news for the cyclist. To protect themselves, cyclists should always wear a helmet, which SETI in 2015 has shown to reduce the risk of traumatic brain injuries. Helmets also use momentum to protect the cyclist. According to the impulse momentum theorem, to change an object's momentum, a force must be applied for an amount of time. The helmet increases the time the force is applied, which reduces the force of impact. Thanks again for listening to this presentation on the biomechanics of cycling. We hope you learned something.